Welcome. My name is Randy Ellis. In this session, we'll go through some of the prerequisites for nonlinear data analysis, and this will be more linear algebra. The main concepts for this session are we'll recall the zero-mean matrix of data and the singular vectors of these zero-mean data. And then we'll reconstruct our data from what are called the principal components. And this will give us axes and scores of our data. Related to this is the scatter matrix, which is very close to the covariance matrix. And this is referred to as principal component analysis, or PCA, and our main use of it is for dimensionality reduction of our data. Vector spaces. Let's just quickly recall the important vector spaces of a full rank matrix. So the column space is where the columns live, the row space is where rows live, and for our data we usually have many more observations than we have variables. Dimensionality reduction is the idea of employing fewer variables than were originally provided. So what that means is we want to have variables that are in a smaller space than the original variables lived in. So the terminology for PCA, it all begins with our zero matrix. So let's recall that our zero matrix, which we're writing as M, is our data minus the mean of the data. And here we're taking the mean of each column, so that's our A bar is an observation. And then the one vector times this gives us the zero matrix, and then this minus that is our zero mean data. So we can use this zero mean matrix to formulate the covariance matrix. And the covariance matrix is defined as the transpose of the zero mean times the zero mean, and then we divide by one less than the number of original observations. So this is the covariance matrix. And in principal component analysis, the loading vectors, that's the name for the eigenvectors of the covariance matrix. So these are, each one of these has n entries, and these constitute a basis for the row space of the covariance matrix. The latent variables, we'll rarely use this term, but if you're coming across PCA, these are the eigenvalues of the covariance matrix, and we'll write these using the symbol lambda. So scores are this. First, let's suppose that we consider that first loading vector, which is the first eigenvector of the covariance matrix of our data, which is derived from the zero mean data. So the weights that this loading vector provide are the entries. So we can think of the entries of this loading vector, which typically has a zero norm, is these can now be considered as weights. And what we could do is we could then weight the first observation of the matrix and so on and so on. And what that would give us is this would give us a number. And this number is referred to as the score for the first component. And we can write this as for each of our I observations, we'll have a score. So we'll say this is Z sub I. So we can then compute all of the scores at once just by saying that the first score vector is the zero mean matrix times the first loading vector. If we want to consider k of these, what we could do is we could take a matrix V, which is the first k loading vectors, and we could combine that into a matrix, and then our zero mean data times this loading matrix will give us a score matrix. So each row of this score matrix is the first score of the data, the second score of the data, and so on until we have k of these. The residual error of regression is something that we've already gone through. We're saying that the residual error is the true value minus the predicted value. Well, suppose that we have data and we have a prediction. What that means is that the first residual error is the difference between, here we have A along the horizontal axis and C along the vertical axis. It's the vertical error between the dependent value and the predicted value, and then the second and the third and the fourth and so on. So that is the residual error that we get from linear regression. Well, what does it look like when we have PCA? Well, what PCA is doing is it's minimizing the orthogonal error to the fit. So instead of going vertically, it's going perpendicularly at each point and saying, what is the orthogonal error? So this is a change. When in PCA we're saying all of the data are independent. In linear regression, we had one set that was special, it was dependent, and the others were independent. But often we get all of the data are independent, and that's where PCA may be appropriate. So what that means is linear regression, instead of doing regression, what we're really doing is we're doing explanation. And Carl Pearson observed this in 1901. He said, suppose you have data and you're trying to perform a regression. Well, what he observed is that you could regress one variable against the other or the other against the first, and each of these would produce different regressions. So here we have a line of regression. So here he's regressing y against x, and here he's regressing x against y. And this middle one, he called the line of best fit, and that is actually coming out of principal components analysis. Principal components analysis, by the way, wasn't invented formally until 1935 or 1936. So the scatter matrix of data is very, very closely related. We'll say that the scatter matrix is just the transpose of the zero mean times the zero mean data. And what that gives us is S is now symmetric by construction, and it will be positive semi-definite. So it will turn out that it has the same eigenvectors as the covariance matrix, but the eigenvalues have now been scaled. So B was the scatter matrix divided by m minus 1, and that means that the eigenvalues of the scatter matrix are m minus 1 times the latent variables of the covariance matrix. So we can think of scatter as being weighted covariance. We use this when the number of observations matters to us. So when we remove this scaling factor, this might turn out to be important in certain data analysis. So the loading vectors are the same, whether we use the covariance matrix or the scatter matrix. They come out of the spectral decomposition, and they are an orthonormal basis. So what these do algebraically is these provide us with new and better coordinates for explaining our data. And geometrically, we can think of these as describing axes of a hyperellipse. So if you scroll back to Carl Pearson's diagram, you'll see that the first loading vector goes through the mean of the data, and it is the axis that, the single axis that best describes that data that he presented in 1901. So what are the relations here? Well, the scatter matrix is the transpose of the zero mean times the zero mean. It has the same eigenvectors, and these turn out to be the right singular vectors. If we take M and we perform its singular value decomposition as U sigma V transpose, and then we do the multiplication, we can see that the scatter matrix is this. And so the square of the singular values of our zero mean matrix are the eigenvalues of the scatter matrix. That means that we can perform PCA not by computing this transpose. All we have to do is take the singular value decomposition of our zero mean data as U sigma V transpose, square those values. That gives us the latent variables derived from the scatter matrix, and the columns of the right orthogonal matrix are the loading vectors for PCA. So in practice, if we have data, we can just take the SVD of the zero mean data instead of going through PCA. So this is often used for dimensionality reduction. These turn out to be equivalent statements. You can use the first k scores of the data of PCA to represent your data. You can use a rank k approximation of your zero mean. Either way, this reduces the dimensionality of the data that you have. It takes it from the original n and takes it down to k. So for example, you might have 20 original variables, and perhaps a scree plot suggests that only 2 are needed to adequately represent the data for your purposes. And we still retain all of the observations. We're not getting rid of them, and we can think of these as being new coordinates, is that the eigenvectors of the scatter matrix are giving us new coordinates to represent our data. So how can we summarize this session? Well, PCA uses either the covariance matrix or the scatter matrix, depending on how you want to interpret those latent variables. The loading vectors are eigenvectors of the covariance matrix. Scores are the zero mean data times the eigenvectors. We can use the singular value decomposition to compute principal components analysis, and PCA is an effective way of reducing the dimensionality of data for data that have a reasonably linear model underlying them.